Some of you might remember talking about an experiment in Physics 20 called the Cavendish torsion balance experiment. It was used to find the value of the gravitational constant. Remember Newton's law of universal gravitation, F is equal to gm1 m2 over r squared. The value of g, 6.67 times 10 to the minus 11, was discovered by using this torsion balance experiment. Today we're going to talk about another experiment that was performed really similar to that Cavendish torsion balance experiment, but this one was performed by a guy named Coulomb, the guy who the unit for charge is named after, and it was used to find a relationship, not so much a value, but a relationship between charges, separation distance, and electrostatic force. So in other words, what's the relationship that shows how charge and separation distance affects the electric force? Here's the essence of how it was set up. And this is a simplification, but it works for us. You've got this rod hanging from the end of a string that's hanging from the top of a box or something, and you've got this ball on either end of this rod. On one end of the ball, on one end of the rod, we're going to call the charge Q1. It's going to be charged. On the other end, it's whatever, it doesn't matter. We're going to bring another charge, Q2, nearby Q1. And we're going to see how it affects it. In fact, we're going to measure the value of Q1 and Q2. We're going to measure the separation distance, and we're going to measure the force. How do we measure the value of Q1 and Q2? Well, this is actually a little bit tricky. When Coulomb performed his experiment, he didn't have any way of actually measuring the exact charge that was present on Q1 and Q2. But what he could do is find relative charges and manipulate relative charges. So in other words, if he had a ball that was neutral, okay, and then he had another one that we had a charge of, let's say, Q, and he touched them, then they became a half Q and a half Q. And then he touched a half Q with neutral, and it became a quarter Q and a quarter Q. And then he touched a quarter Q with neutral, and it became an eighth Q and an eighth Q, and so on. So he was able to manipulate the value of the charges without knowing exactly what the charges were in coulombs. That's okay. He wasn't trying to find a value, he was trying to find a relationship. So he was able to find a relationship by manipulating those values. So that's how he gets Qs. The distance, he's able to measure easily by just physically using something like a ruler to measure the distance that separates these charges. The force, another tricky one. The electrostatic force of either attraction or repulsion, depending upon what type of charge we have, is measured by the amount of twisting of the string. This string right here is going to twist when these charges attract each other or repel each other. And we measure the amount of twisting, that's going to be an indication of the value of the force. It's kind of like you go on a swing set, not today, because it's 0 and snowing today, but on a nicer day, like Friday when it's supposed to be plus 20, you go on that swing set, and what do you do when you're on that swing set? Usually at some point you end up twisting it around, right? So that when you let it go, it ends up spinning you around quickly. You know intuitively when you do that, intuitively, you know that the more you twist it, the more force it requires, the harder it is to do it, right? Coulomb would have done something like that with this string. He would have done experiments to determine how much force was required to twist it a certain amount. And then, when he does this experiment here, he looks at how much the string is twisted, and he knows from that how much force must have been applied to it. So he's able to measure the charges, he's able to measure the separation distance easily, and then he's able to measure the force by using the amount of twisting of the string. Torsion, by the way, means twisting. So we talked about the torsion balance experiment, the twisting balance experiment. Now, how does this experiment go? Well, essentially, he does 3 different experiments. Okay, in the first one, I don't know what order it would have been done in, but let's say in the first one, he would manipulate the value of Q1. The responding variable would be the force. So how does Q1 affect the force? And the control variables would be, what would the control variables here be? If he changes Q1 and measures the force as a result of that, what would the control variables be? What would you have to keep constant here? Julia? Good. R and Q2. You'd have to keep the same there. Now, there's other ones as well, but we talk about this when we're doing experiments, right? What do I care about when you have to list the variables? The really important ones. What are the really important ones here? R and Q2. So he plots a graph, gets some data for Q1 and F, plots a graph of F versus Q1, and he gets what amounts to be pretty close to a straight line. That tells him that F, or at least the magnitude of F, is directly related to Q1. Do you guys recognize that symbol there? F is not equal to Q1. F is related to Q1. So in other words, if Q1 goes up by a factor of 4, then F goes up by a factor of 4. We don't know the values, but we know that they're directly related to each other. So then he does another experiment. This time he manipulates Q2, and he sees how F responds to that. What does he got to control this time? Well, the other ones, right? Q1 and R. Plots a graph of force versus Q2 this time. Guess what he gets? Straight line. Tells him that F is directly related to, not equal to, but directly related to Q2. So as Q2 goes up, F goes up. As Q2 goes down, F goes down. And finally, what's he going to manipulate this time? What's left? He's going to change the value of R. How does R, the separation distance, the distance between the two charges, how does that affect the amount of force? How do you think it is going to affect the amount of force? Bigger separation distance, bigger force, or smaller force? Smaller force, right? The further away the two things are that are interacting with each other, the smaller the interaction is going to be. The responding variable is force, and the control variables this time would be Q1 and Q2. You'd have to keep both of those values the same. You plot that graph of F versus R, and the shape of that would be this. Now that shape could mean 1 over R, or it could mean 1 over R squared. In this case, it would mean F is related to 1 over R squared. But it would be difficult to tell just by looking at it whether it was 1 over R or 1 over R squared. You're going to do an activity tomorrow, actually, where you're going to find these relationships yourselves on a little simulation, a little computer simulation. You're going to plot these graphs, and you should end up with this graph for F versus Q1. You should end up with this graph for F versus Q2, and you should end up with this graph for F versus R. Now, he puts them together. Right? He finds the relationship between F and all three of these variables. He puts them together. And he gets a law that we call Coulomb's Law. It says F is related to Q1, but it's also related to Q2, and it's also related to the inverse square of R, the separation distance. That's not an equation, but it's close. It's related to that term. It's equal to this term. A constant or a number k times Q1, Q2 over R squared. Does this equation look familiar to you at all? Where have you seen this equation before, Isaac, or something like this equation? Yeah, F is equal to G times M1 times M2 over R squared. That was Newton's law of universal gravitation. The force that acts between two objects with mass is equal to a constant G times M1, M2 over R squared. The force that acts between two charges is equal to a constant K times Q1, Q2 over R squared. So fundamentally the same structure of the equation, some different variables, but same structure for sure. Does anybody remember what the value of G was? Check your data sheet. What is it, Isaac? You're close. 6.67. times 10 to the minus 11. It would be Newton meter squared per kilograms squared. You know what the value of K is? 8.99 times 10 to the positive 9 Newton meter squared per Coulomb squared. All other things being equal, which do you think is a bigger force? The electric force or the force of gravity? The electric force. Look at the constant. The constant is 10 to the 20 times bigger. Now that doesn't mean the force is always 10 to the 20 times bigger, but you can see the electric force certainly has a leg up with a constant that's 10 to the 20 times bigger. Generally speaking, okay, if there's any charge present, the electric force will be stronger than the force of gravity. Here's a little summary of those two forces that we just talked about. We call both of them inverse square relationships. That just means that F is inversely related to the square of the distance. In other words, as distance between the masses, distance between the charges goes up, the force goes down. As R goes down, F goes up. Coulomb's law is generally a bigger force. It has a constant that's 10 to the positive 9. Newton's force, or the force of gravity, is generally a pretty small force. It has a constant of 10 to the minus 11. And in terms of direction, here's a big difference, actually. Gravity is always attractive, at least as far as I know. Gravity always attracts things. Whereas the electric force, the Coulomb's law force, attracts things if they're opposite charges, but it repels things if they're like charges. Let's take a look at one example and we'll finish off the day with this. It says a metal sphere with a positive charge of 5.5 times 10 to the minus 7. Notice 10 to the minus 7 because a Coulomb is so big. We're not usually dealing with charges that big. 10 to the minus 7 seems reasonable. And this mass is separated from an identical metal sphere with a negative charge of 2 times 10 to the minus 7 coulombs by a distance of 5 centimeters. Circle that because we've got to be in meters. What's the electric force on the positive charge and the electric force on the negative charge, and what's the acceleration of the positive charge? We're going to say Q1 is 5.50 times 10 to the minus 7 coulombs. We're going to say Q2 is 2.00 times 10 to the negative 7, but it's negative. We should have actually circled that. That was a negative charge. My separation distance R is 5 centimeters or 0.050 meters. I'm not going to forget to convert that to meters because I circled it in red. We want to find the force here. Now, the force is KQ1 Q2 over R squared. 8.99 times 10 to the 9 times, now pay attention to this, okay? Pay attention to this. 5.5 times 10 to the minus 7 times 2 times 10 to the minus 7. Does that make sense? Shouldn't it be negative? No. We're actually going to drop the sign of the negative. Whenever we plug a charge into an equation, we want to drop the sign. Here's why. For us, when we get an answer for any question, we get an answer. We want positive and negative to mean direction. If I plug a negative into this, it's not going to mean left. I'm going to get a negative force, but it's not going to mean a force that's to the left or south or down. Okay, we want it to mean that. So what I'm telling you to do is drop the sign of the charge when you're plugging it into an equation. Don't ever use the sign of a charge in an equation. R is 0.050, and then we've got to square that. So let's figure out this force now. We got 8.99 times 10 to the 9 times 5.5. Can we cancel out, by the way, that 10 to the minus 7? It's in both terms, right? But it doesn't appear in the term on the left-hand side, the force, so we can't do that. Times it by 2 times 10 to the minus 7. And then we're going to divide it by 0.05 squared. 0.39556, 0.396. Yeah. All right, so what's the force on the positive charge? 0.396. What's the force on the negative charge? 0.396. Object A applies a force on B, object B applies an equal and opposite force on A. Finally, what's the acceleration of the positive charge? Whenever you're trying to find an acceleration in physics 30, just say F over m. The mass was, what was the mass? 2.5 times 10 to the minus 3. Uh, 158 or 1.6. Notice this is 2 digits because the mass only had 2 digits, but the force was 3 digits because we didn't use the mass in calculating the force. Sorry? Yeah, meters per second squared, yes, thank you. So my units are wrong there, but I think my answer's right. Good. Let's go worksheet number 6, questions 1 to 5.